Welcome to the deep dive. We're here to really extract the crucial insights from a sea of information, hopefully leaving you feeling informed and maybe having one of those aha moments.
That's the goal.
Today, we're digging into smart hospitals, exploring how they're actually becoming a reality.
Yeah, it's fascinating stuff.
If you're like us, you appreciate learning efficiently, and, well, that efficiency is kind of revolutionizing healthcare right now.
Exactly. We've got some really interesting material showing how artificial intelligence, AI, and digital transformation are not just tweaking healthcare.
No.
No, they're fundamentally reshaping how hospitals work, how they deliver care. It's a big shift.
Okay, so our mission today, and you've basically accepted it by tuning in, is to distill the core ideas, look at the practical uses and, the exciting potential of AI in modern medicine,
Right. We'll start with the basics, the foundational concepts of AI in this healthcare space.
and then journey through to what the future might hold.
Precisely. All aiming for those key aha moments for you, the ones that really stick.
And we know you listening come from all sorts of backgrounds, some techie, some not.
So we promise to keep this clear, keep it engaging, no overwhelming jargon, just the insights.
Okay, let's unpack this then. When we talk about artificial intelligence in healthcare, what are we really discussing beyond, the image of robots everywhere?
Well, at its core, AI is about creating machines capable of tasks that normally need human intelligence.
Like processing data,
Yeah,
making decisions.
exactly. Processing vast amounts of data, making reasoned decisions. The material we're looking at even calls it a new intellectual paradigm.
A paradigm shift. That sounds significant.
It is. It signals a fundamental change in approach, moving away from just treating illness.
Towards predicting and preventing it.
Precisely. And a key part of this is machine learning. The real insight there is how algorithms can learn on their own to spot disease patterns, predict outcomes from huge data sets.
Often better than humans, at least in terms of scale.
Yes, often exceeding human capabilities in sheer scale and consistency.
Wow, that proactive approach really does sound like a game changer. So what's the main driver? What's the central purpose or maybe calling of AI in medicine?
According to our sources, it's pretty comprehensive. Obviously, it's about using these intelligent algorithms to improve diagnosis, improve treatment. That's key.
But there's more to it.
Oh, yeah. It's also fundamentally about cutting down on human errors, which unfortunately do happen, and boosting the overall efficiency of the whole healthcare system.
And you mentioned something about access.
Right. There's this underlying goal, almost a justice-oriented perspective, aiming for fairer, more equal access to advanced medical care for everyone.
Fair access. That's powerful. How can AI actually help achieve that?
Well, think about AI's ability to analyze data from, well, everywhere and spot patterns a single doctor might miss.
Okay.
This could lead to earlier diagnoses, more accurate ones for a much wider group of people, regardless of, say, where they live or if they can easily get to a specialist.
Makes sense. The document also talks about mission versus vision.
Yes, it draws a distinction. The mission is about what AI is doing now in medicine, things like personalized treatment, ensuring data security, dealing with ethical questions.
The practical current stuff.
Exactly. And the vision is where it's heading, the future picture. Hospitals as smart leading medical centers, both nationally and internationally.
Right. Mission,
Yeah.
the why, and what now. Vision,
Yeah.
the where to next. Got it. So what are the basic building blocks, the key areas of AI making this possible in healthcare?
Okay, there are several core areas. First, machine learning, which we touched on. Systems learning from data without being explicitly told how.
Like the spam filter example.
Exactly like that. It learns what's junk by seeing patterns in millions of emails. Then you have reinforcement learning.
That's learning by trial and error.
Basically, yes, learning from rewards and penalties. Natural language processing, NLP, that's crucial for machines to understand and interact using human language.
Like analyzing doctor's notes or chatbots.
Precisely, or voice assistants. Then computer vision. This lets machines see and analyze images and videos.
Which is huge for medical scans, I imagine. CTs, MRIs.
It's absolutely critical for interpreting those. Regression models, which are part of machine learning, help predict continuous things, like how long recovery might take.
And tree-based models.
They're really good at classifying conditions based on various factors.
So computer vision gives AI eyes for medical images. What else?
We also have automation and robotics. This covers everything from robots delivering meds around the hospital to actually assisting in complex surgeries.
Okay.
Neural networks are next. These are models inspired by the human brain, really good at finding complex patterns in data.
Brain-inspired. Interesting.
And finally, underpinning all of this are complex algorithms. These are the mathematical instructions, the recipes that let AI tackle these really intricate medical problems.
Okay, that gives us a solid map of the AI toolkit. Now, how did we get here? How has AI in medicine actually, evolved? Our source mentions 4 distinct generations.
Yeah, that's a helpful way to frame it. The document outlines 4 generations, showing a progression, really, of increasing sophistication over time.
So where did it start? Generation 1.
The first generation. Think 1970s through the 1990s. This was all about expert systems,
Expert systems meaning.
meaning they were designed with predefined rules, usually gathered from human experts, to help with diagnosis and treatment decisions.
Any famous examples?
Yes, MYCIN is the classic one. It was developed to diagnose bacterial infections, specifically blood infections, and suggest treatments.
So the key insight then was just proving AI could even assist with diagnosis using rules.
Exactly. It showed the concept worked. But its rigidity, the fact it couldn't learn, really highlighted the need for something more adaptive.
So MICIN was basically like a big, complex digital flowchart based on medical textbooks.
You could put it that way, yeah. It followed rules. If symptom A and test result B, then likely condition C. It could offer treatment suggestions based on that fixed knowledge base, but, and this is the big limitation, it couldn't learn anything new. It was stuck with what the humans initially programmed into it.
Right. The source gives an example.
It does. A simple one. Patient has a high fever, high white blood cell count, and tests show gram-negative bacteria. The system's rule might say, high probability of E. coli infection, recommend the antibiotic gentamicin.
Straightforward, but yeah, inflexible. What came next? Second generation.
Right, the second generation, roughly the 1990s up to the 2010s. This is where classical machine learning really came into focus for medicine.
So shifting from fixed rules to learning from data.
Exactly. The emphasis moved to algorithms that could actually learn from medical data to make predictions, find patterns, offer insights.
What kinds of algorithms are we talking about?
Things like regression analysis, decision trees, support vector machines, SVMs, and k-nearest neighbors, or KNN,
The applications.
predicting the likelihood of diseases, diabetes, heart attacks, that sort of thing. Also, classifying patients based on their clinical data.
So the big leap forward was better analytical power, being able to learn from the data itself.
Definitely improved analytical capabilities. But there was a significant drawback. It often required a lot of feature engineering.
Meaning humans still had to do a lot of prep work.
Yes. Experts had to manually figure out and prepare the important data features before the algorithms could learn effectively. And it still wasn't great with complex, unstructured stuff like medical images.
Okay, that makes sense. Which naturally leads us to the third generation, deep learning. Started around 2010, still ongoing.
That's right. And this is where many feel AI in medicine really took off.
Because it could handle that complex data.
Precisely. The key insight of deep learning was its ability to automatically learn complex features directly from raw data, like images or signals, without needing that manual feature engineering.
Unlocking much higher accuracy, I bet.
Yes, unlocking unprecedented accuracy, especially in areas like radiology analyzing scans for cancer detection, for instance.
So what technologies are powering this?
Deep learning uses these multi-layer neural networks. You hear about algorithms like CNN's convolutional neural networks.
Good for images.
Exactly. And RNN's recurrent neural networks, or their more advanced cousins, LSTM's long short-term memory networks.
Those are better for sequential data, like signals over time.
Correct. Analyzing things like ECG heart signals or trends in patient records. Also, Jan's generative adversarial networks.
We'll come back to those. So the big applications here are things like cancer detection and scans, ECG analysis, even NLP on patient notes.
All of those. It's been huge for image analysis, signal processing, and understanding text data in healthcare. The core power is automatic feature extraction from all sorts of medical data.
The big advantage then? High accuracy, no need for manual feature fiddling.
That's the headline. The main challenge, though.
Let me guess. Needs tons of data and computing power.
You got it. Deep learning models are data hungry and computationally intensive to train properly.
Okay, and that brings us up to today, or almost. The fourth generation, explainable and autonomous AI, starting around 2020, still under development.
Yes, this is really the cutting edge, the next frontier. The main focus here is twofold. First, AI that doesn't just give an answer, but explains why. That's explainable AI, or XAI.
That sounds incredibly important for medicine.
It is. The other focus is on self-learning AI, sometimes called auto-ML, making AI model creation more automatic, and a huge emphasis on human-machine collaboration.
So doctors and AI working together, but transparently.
That's the idea. Explainability is absolutely critical here.
Why the big push for explainability now?
Well, our source points out that many earlier deep learning models, despite being accurate, are often seen as black boxes.
Meaning you get an answer, but you don't know how it got there.
Exactly. And in a high-stakes field like medicine, just getting the what isn't enough. Doctors, patients, regulators, they need to understand the why behind a diagnosis or a treatment recommendation.
For trust, right,
Yeah.
and safety.
Absolutely. XAI aims to make the AI's reasoning transparent. Let humans see the basis for its conclusions.
That would definitely help build trust and allow for proper human oversight.
Precisely. The benefits listed are clear. Increased trust, obviously.
Yeah.
Better ability to spot potential errors or biases in the AI model itself.
Helps with regulations too, I imagine.
Yes, ensuring ethical compliance. And interestingly, it might even help doctors discover new medical insights by seeing the patterns the AI highlights.
The document gives a medical example.
It does, a good one. A traditional AI might just say cancer positive, simple output.
Okay.
An XAI model, though, could provide much more detail. Like, based on the lesion size here, the change in cell density noted on the scan here, and considering the patient's smoking history, there's a 92% probability of lung cancer.
Wow. That's a world of difference.
Yeah.
That level of detail and transparency changes the whole interaction.
Completely. It becomes a tool that collaborates with the clinician, providing evidence.
And the autonomous part of this fourth generation, what does that refer to?
That points to AI's growing ability to learn and adapt more independently, and also the really exciting potential for AI to start generating and simulating medical data.
Generating data? For what?
Think about drug discovery, simulating how molecules might interact, or modeling how diseases might spread or progress. That could be revolutionary.
Okay, so we've tracked this evolution. Rules, then learning from data, then deep learning on complex data, and now explainable, collaborative, even generative AI.
It
Fascinating.
really is a rapid progression.
Now, our source also distinguishes AI types based on capability. Narrow AI versus artificial general intelligence. What's the core difference?
Yeah, this is a fundamental concept. Narrow AI, often called ANI or weak AI, is what we mostly have today. It's AI that excels at one specific task or a narrow range of tasks.
Like the image analysis AI we talked about.
Exactly. Or playing chess or filtering spam. Our source notes, it has poor memory in a general sense. It doesn't transfer learning easily. It performs well only within its specific training domain.
The specialist tool.
A highly specialized tool, incredibly effective for its purpose, but you can't ask a radiology AI to manage hospital logistics. Most medical AI applications now, image diagnosis, record management, fall under ANI.
And they improve quality and accuracy within those limits.
Significantly. They reduce errors, aid doctor decisions, boost efficiency in their niche.
Okay, so if narrow AI is the specialist, what's artificial general intelligence, or AGI, the generalist?
AGI is the goal, really. The concept of AI that can perform pretty much any intellectual task a human can. It's about creating systems with human-like intelligence across the board, independent thinking, reasoning, learning across different areas.
That sounds more like science fiction AI. Does the source give examples?
It gives a broad example, like managing an entire complex organization, the Motor Human Resources Management Organization mentioned. In medicine, the potential applications are vast.
Such
Processing all kinds of diverse medical data to optimize surgical techniques, using advanced 3D imaging for super precise surgery, analyzing scans and patient history to diagnose complex cases, generating detailed reports, even figuring out optimal treatment doses.
much broader capabilities.
Yeah.
Are there any real-world systems today that are considered examples of AGI or at least strong AI in medicine?
The document does point to a couple: the Da Vinci surgical robot,
Yes, heard of that. Made by a U.S. company.
Intuitive Surgical, yes, and also the Manus system, which comes from Chinese companies. These are highlighted as examples of strong or general AI operating in the medical field now.
Interesting. What makes the Da Vinci robot qualify as AGI in this context? It's still assisting a surgeon, right?
It is, but the AI embedded within it is doing quite a lot. It processes huge amounts of surgical data in real time to actively optimize the surgeon's movements.
Okay.
It enables those incredibly precise, millimeter accurate robotic arms. It integrates sophisticated 3D visualization, and it analyzes patient data during the procedure to help reduce errors.
So it's doing more than just translating the surgeon's hand movements.
Much more. It's actively processing, optimizing, and enhancing the procedure based on data. The result is less invasive surgery, often with better outcomes, faster recovery.
Right. And the Manus system from China, what are its key features?
Manus is described as an AGI system with, again, a broader range of capabilities than typical narrow AI. In medicine, it's reportedly used for high accuracy diagnosis by analyzing lots of different data types together.
Okay.
Also, advanced image processing, CT, MRI, optimizing hospital-wide processes like resource allocation, scheduling staff.
So operational stuff too.
Yes. And providing sophisticated decision support for personalized treatment plans. It even tries to predict treatment trends based on historical data analysis.
That's a really wide scope.
Yeah.
So given these examples, Da Vinci, Manus,
Yeah.
would you say smart hospitals are truly becoming a reality now, not just a future concept?
Well, the document suggests that while, complete predictability or full autonomy in every single medical scenario isn't here yet,
Understandable.
the improvements are very real and tangible now. We're seeing significant gains in healthcare quality, better diagnostic accuracy, fewer medical errors, smoother hospital operations, and smarter resource use, all thanks to these technologies.
So it's definitely moving beyond theory into practice.
Absolutely. The impacts are being felt.
Speaking of practice, the document gives some concrete examples of hospitals around the world that are leading this smart transformation. Let's look at those.
Sure. In the U.S., Johns Hopkins Hospital is mentioned. They're using AI for medical image analysis, better patient record management, and optimizing surgeries. The source puts them in that AGI ANI Generation 2 category.
Okay. And elsewhere.
King's College Hospital in England. They're using the Internet of Things IoT for real-time patient monitoring, continuous health tracking with immediate alerts if something's wrong. They're listed as AGI ANI Generation 3.
Real-time monitoring. That's powerful. Any others?
Asuda Medical Center in Israel, they're using surgical robots, maybe like Da Vinci, and machine learning for highly personalized treatment plans. That's categorized as AGI NNI Generation 4.
Interesting how they fall into different generations based on their focus. What about China? You mentioned Manus.
Yes, China is highlighted as a leader here, really pushing digital transformation in hospitals. They're apparently widely using automated robots for things like delivering drugs,
Wow.
sophisticated AI for diagnosis, and various health monitoring apps and systems. The source just lists them as AGI, suggesting quite broad integration of this more general AI across their healthcare system.
A global trend then, but maybe with different paces and focuses. We talked about Da Vinci, but the source adds more detail on its hospital impact.
It does. It really exemplifies how AGI is making surgery less invasive and more precise, developed by Intuitive Surgical, as we said.
Minimally invasive is the key phrase, right?
Absolutely. Tiny incisions, but the surgeon has incredible dexterity and control via the robotic arms and console. The precision is remarkable.
Better than human hands alone.
Often, yes, in terms of eliminating tremor and allowing finer movements in tight spaces.
Yeah.
This leads to shorter surgeries sometimes, definitely faster recovery, fewer complications usually.
And the AI is crucial.
Totally integral. Processing surgical data to optimize movements, ensuring that submillimeter accuracy, providing that detailed 3D view, analyzing patient data on the fly to flag potential issues. It's a step change in surgical capability.
Okay. And the Manus in China, the document stresses its wide applicability.
Yes, it's presented as a really versatile AGI system, tackling lots of different medical challenges, high accuracy diagnosis from complex data, advanced image processing, optimizing hospital operations like scheduling and resource use.
The management side again.
Right. Decision support for personalized treatments, predicting treatment trends. The advantages listed are significant. Better diagnosis, personalized medicine, smarter hospital management, reducing errors and waste.
Predicting disease outbreaks too.
Yes, potentially analyzing public health data for that. And again, like Da Vinci, reducing surgical errors, enabling minimally invasive procedures, speeding up recovery.
It's clear these AGI-level systems are having a major effect. Now, the document also briefly mentions artificial superintelligence, ASI. That sounds
Yeah.
beyond AGI.
It is. ASI is definitely theoretical, future gazing territory right now. It's the idea of AI that doesn't just match human intelligence, but significantly surpasses it across essentially all cognitive domains.
Smarter than humans in every way.
That's the concept. Processing information at speeds and complexities we can't even comprehend, learning exponentially, making decisions far beyond our capacity.
That feels very far off from medicine. But are there potential applications people are thinking about?
Even though it's distant, the document suggests some transformative possibilities. Imagine diagnoses that are far more accurate and catch diseases incredibly early.
Okay.
Highly precise predictions of disease progression and treatment response, discovering completely new drugs by simulating molecular interactions at vast scale.
Drug discovery seems like a big one.
Huge. Robotic surgery with levels of precision and autonomy that are hard to picture now. Even managing global pandemics or large-scale health crises with unparalleled foresight and efficiency.
It's aiming to overcome our current human limitations in understanding and tackling complex health problems.
That's the idea behind ASI, yes.
Fascinating, if a bit daunting. But let's bring it back to the present. What about the challenges? Implementing these smart hospitals widely can't be easy.
No, absolutely not. The document is clear about the hurdles. Patient data security is a massive one. Medical data is incredibly sensitive.
Needs ironclad protection.
Absolutely. Advanced security is non-negotiable. Then there's integration. Trying to mesh these cutting-edge systems with existing, often much older, hospital IT infrastructure, that's a real headache.
Compatibility issues.
Big time. And training. Doctors, nurses, all the staff need to be comfortable and competent using these new AI tools. That requires significant investment in education and change management.
Can't just drop it in their laps.
Definitely not. And then, overarching everything are the ethical issues, especially around diagnosis and treatment decisions made by AI. How much human oversight is needed? Who is responsible if something goes wrong?
Really critical questions. Our source even mentions top hospitals like Mayo Clinic and Johns Hopkins grappling with these challenges.
Yes. Even the leaders, the ones pushing the boundaries with advanced AI, smart records, data-driven diagnosis, command centers for managing beds and ambulances, they're all actively working through these security, integration, training, and ethical challenges right now.
It's an ongoing process for everyone.
Very much so.
Okay, so we've covered foundations, evolution, capabilities, examples, challenges. Let's get a bit more technical for a moment. The document dives into specific learning models within AI and how they're used in medicine. This really shows the variety of tools available.
It does. It breaks them down nicely. Under the big umbrella of machine learning, the first category is supervised learning.
That's learning from labeled data, right? Input X gives output Y.
Exactly. You show it examples. This includes algorithms like linear regression, good for predicting continuous values.
Like recovery time.
Yep, predicting recovery time based on history, severity, treatment. Or predicting trends in hospital admissions. Example given. Predicting recovery time after heart surgery using age, blood pressure, heart damage level.
Makes sense. What else in supervised?
Logistic regression. That's for binary classification, yes, no, sick, healthy. Used a lot for detecting disease presence, like diabetes or hypertension, based on risk factors, or predicting critical conditions like septic shock.
Giving warnings based on probability.
Exactly. Then, multinomial logistic regression handles classifying patients into multiple categories based on symptoms, like is it flu, COVID, or just an allergy based on fever, cough, etc. Helps guide doctors.
Okay.
Naive Bayes, that's often used for rapid diagnosis based on early symptoms using probability theory. Again, maybe calculating the likelihood of flu versus COVID based on initial presentation.
Faster initial assessment.
Right. Support vector machines, SVMs, powerful for medical image analysis, separating cancerous from healthy cells in an MRI, for instance. Also good for classifying patients by risk level.
Image analysis keeps coming up.
It's a huge area. Polynomial regression handles more complex, nonlinear relationships, maybe predicting blood sugar fluctuations in diabetics. Decision trees. Very intuitive. Used for diagnosing chronic diseases based on symptoms and history, like assessing diabetes risk, using age, blood sugar, family history. Also for classifying patient conditions.
Like a flowchart again, but learned from data.
Sort of, yes. Random forests improve on single decision trees by combining many of them. Good for improving prediction accuracy, like forecasting needs for hospital equipment ventilators, ICU beds based on attendance patterns, disease data.
Ensemble methods.
Exactly. K nearest neighbors, KNN. This classifies a new patient by looking at the Kamen's most similar patients in the database, useful in emergencies like assessing heart attack probability by comparing symptoms to known cases.
Using past experience.
Right. XGBoost often wins data science competitions. Good for predicting treatment success, helping choose the best strategy based on patient history, like predicting chemotherapy effectiveness.
Powerful predictor.
And lastly, under supervised here, ARIMA. That's specifically for time series analysis, things that change over time. Used for accurately predicting things like hospital bed occupancy rates in the future.
Quite a toolkit just within supervised learning. What about when you don't have those nice, neat labels on your data?
Then you move into unsupervised learning. The goal here is different. Find hidden patterns, structures, groupings within unlabeled data.
Discovering insights without being told what to look for.
Exactly. A key technique is dimension reduction. Algorithms like PCA principal component analysis, or TSNE, these help simplify massive, complex medical data sets.
Why simplify?
Makes analysis faster, more manageable, easier to visualize. You remove redundant information, focus on the most important underlying patterns or features. Think huge MRI data sets or complex genetic data.
So PCA finds the main ingredients in the data?
Kind of. It transforms the data into principal components, capturing the most variance. Useful for faster image analysis, optimizing treatment predictions, analyzing equipment data patterns.
Okay. What else in unsupervised?
K means clustering. This groups similar data points together. In medicine, you could group patients based on symptom similarities or group them by health data profiles, useful for finding patient subgroups.
Like grouping diabetes patients for tailored treatments.
Perfect example. Or separating patients into different risk levels for resource allocation.
Makes sense.
DBSCAN is another clustering method, good at finding unusually shaped clusters or identifying outliers. Could flag a sudden spike in patients in one department, for instance.
Spotting anomalies.
Right. You can also apply clustering to laboratory data. Grouping medical test results by patterns might reveal hidden disease risks, like finding clusters in blood tests that correlate with heart or kidney disease risk in diabetics.
Finding patterns in the numbers.
And feature extraction in an unsupervised way means automatically identifying the most vital features within patient data, again, for faster, more accurate processing later on, like automatically pulling out key tumor characteristics from images.
So unsupervised learning is about exploring and structuring the data from within.
That's a good way to put it. The document also briefly mentions semi-supervised learning.
What's that? A mix.
Exactly. It uses a small amount of labeled data combined with a large amount of unlabeled data. It's a pragmatic approach when getting lots of labels is hard or expensive.
Like for rare diseases where you don't have many diagnosed cases.
Precisely. It tries to get the best of both worlds.
Okay, makes sense. We're covering a lot. What about reinforcement learning, RL? How does that fit in?
RL is different again. Here, the AI agent learns by doing. It interacts with an environment, takes actions, and gets rewards or penalties based on the outcomes. No labeled X and Y inputs.
Learning from consequences.
Exactly. Q-learning is a classic RL algorithm. It could be used, say, to optimize hospital resource management, figuring out the best way to allocate beds to minimize wait times or manage pharmacy inventory. The AI learns the optimal policy.
Trial and error to find the best strategy.
Yes. Another one is SARSA. This could be used to dynamically adjust a patient's treatment plan. The AI learns based on how the patient responds, selecting the best next step based on the current state and past effectiveness.
Like adjusting insulin dosage for a diabetic based on real-time glucose readings and past responses.
That's a great potential application. The AI learns the optimal control strategy through experience.
Fascinating. It learns by interacting with the real world or a simulation.
Okay, and finally, we circle back to deep learning.
Yes, using those multi-layer neural networks for the really complex stuff. We have artificial neural networks, ANNs more generally, for analyzing diverse medical data and predicting disease trends based on records, lab results, etc., maybe assessing diabetes progression.
Okay.
Then convolutional neural networks, CNNs, which we stressed for images, diagnosing diseases from MRI, CT, radiology scans, even creating those 3D digital twin models of organs like the heart, detecting tumors with high accuracy.
Still key for visual data.
Absolutely. Feed-forward neural networks can be used for initial disease analysis and diagnosis based on health data, perhaps suggesting initial treatment paths for diabetes or heart disease from lab results.
Initial assessment. Right. Recurrent neural networks, RNNs, and especially LSTMs, long short-term memory, are vital for sequential data.
Things that happen over time.
Exactly. Analyzing heart signals, ECGs, tracking patient conditions via records over time, predicting changes in vital signs for ICU patients. LSTM is particularly good at remembering information over longer periods.
So predicting trends in heart rate, blood sugar, oxygen levels.
Yes, or even predicting patient volume for the hospital, or forecasting epidemic trends based on time series data.
Very powerful for forecasting. And generative adversarial networks, GNs, you mentioned them earlier.
Right, GNs.
Yeah.
That clever setup with the generator network creating data and a discriminator network trying to spot the fakes.
What are the medical uses?
Generating synthetic medical images, this is useful for training other AI models when real data is scarce or has privacy issues.
Creating more training examples.
Exactly. Also, creating automated medical reports using NLP capabilities similar to GPT. Potentially generating ideas for new drug molecules by simulating reactions, or simulating how diseases behave to predict outbreaks.
That generative power is really interesting. And that leads nicely into natural language processing, NLP, and models like GPT.
Crucial area. NLP enables computers to understand and work with human language, reviewing patient records automatically, extracting key information, automating communications like appointment reminders.
Improving medical translation. Analyzing reports for patterns.
All of that. Processing lab data notes into intelligent digital files. And GPT takes it further, producing accurate reports, summarizing long texts, processing patient-doctor conversations.
Powering smarter medical chatbots.
Yes, optimizing chatbots, even suggesting personalized treatments by synthesizing information from vast amounts of research papers, providing initial consultations, processing health data for preliminary diagnoses.
It's bridging the gap between structured data and human language.
It really is. And the document mentions hybrid algorithms too, like the TIRI WS system for septic shock, which combines regression, neural nets, and decision trees for early warnings.
Combining strengths.
And we can't forget the role of computer vision throughout many of these. Identifying tumors, lesions, fractures in X-rays, CTs, MRIs, it's fundamental.
This has been an amazing tour through the AI toolbox for healthcare. So let's try to summarize. What are the big picture benefits, the main applications driving these smart hospitals based on our sources?
Okay, the key benefits really boil down to a few core areas. First, improved healthcare quality. That means more accurate diagnosis, earlier detection, and more personalized treatments that work better for the individual.
Better outcomes.
Exactly. Second, much better patient information management. Faster, secure access to complete records, fewer errors, which boosts patient safety.
Efficiency and safety.
Third, increased productivity and reduced costs. Optimizing hospital workflows, allocating resources better, even managing energy use more efficiently. Less waste, lower costs.
Good for the system.
Fourth, workflow automation. Simplifying routine tasks for staff, freeing them up for direct patient care where the human touch is essential.
Thus burnout, maybe.
Hopefully. Fifth, an improved patient experience. Things like easier online scheduling, being able to track your treatment progress, getting smart notifications, more convenient, less stressful.
Patient-centric.
Also, real-time data access for doctors means more informed decisions made quickly. And finally, as mentioned before, greater hospital data security using advanced protection methods.
That's a compelling list of advantages. And the main ways AI is being applied to achieve these. The key applications.
The document highlights several main areas: advanced diagnostic systems, using AI for image analysis, predicting disease risk early on, that's huge.
Diagnosis is key.
Then optimizing medical records. Digitization, intelligent analysis for quick access, smart scheduling and managing patient flow, predicting bottlenecks, intelligent queuing to reduce wait times,
Improving efficiency.
automating aspects of intensive care and patient monitoring with automatic alerts and smart sensors, surgical robots like Da Vinci and other assisted therapy robots.
The robotics side.
Medical chatbots for online counseling, medication guidance, answering common questions, analyzing medical data on a large scale to spot treatment trends, predict disease patterns, forecast epidemics, help with hospital planning,
Beta insights.
even things like intelligent fraud detection in insurance claims, and developing smart systems for the pharmacy, managing equipment, energy use, parking, information kiosks, tracking patients within the hospital. It's really broad.
It really is touching almost every part of how a hospital runs. From the foundational algorithms we talked about, all the way to things like Da Vinci, Manos, and even looking towards future possibilities like ASI. It's evolving incredibly fast.
Absolutely. And the common thread, the overarching goal we've seen, is always about improving efficiency, boosting accuracy, and ultimately lifting the quality of patient care.
which aligns perfectly, I think, with your desire listening in for knowledge that's both deep and genuinely impactful.
Hopefully, we've delivered some of those aha moments today.
So, as we wrap up this deep dive into the fascinating world of smart hospitals, here's maybe a final thought for you to mull over. Considering this rapid pace of change, the AI, the digital transformation we've explored, how might the actual roles, the day-to-day work of human doctors, nurses, and other medical professionals evolve within these increasingly intelligent hospital environments?
That's a big question. How does the human role adapt and perhaps become even more critical in new ways?
Definitely something worth pondering as we look ahead. Thank you for joining us on the deep dive.